Go.
Hello, my dear students. I want to do another lab with you today. It's lab 3.4. You'll find it posted in the course stream and in your course assignments. This lab, again, involves measurements and density and just reviews some simple concepts and gets you familiar with using the measurements and working with density. And ideally, if we were face to face and able to do so, working with different laboratory equipment, which I'm going to introduce. So this one is one where we would go to the lab, don our safety equipment. I don't really need a lab coat for this, but it makes me look very professorial. And of course, you would all be wearing your safety glasses. And the first part of the procedure asks you to measure 50 drops of water. Measure the mass of 50 drops of water. So I'm going to do that. I have a balance here. I'm going to use this one because the lit up screen on it allows better photography. And I have a small, we call it a portion control cup. You'll see I hand out chemicals and things in small portions and control the portions in them. And when I put on, it's 1.3 grams. And now I need to put 50 drops in it and then weigh it again. And one thing I can do is subtract the difference. It's called weighing by difference. But another thing I can do is I can just hit this button that says tare, and it's T-A-R-E. And when we tare something, we subtract the initial weight, typically the weight of the container. Okay? So I just tared my balance. These are really nice balances. That's a nice feature. I don't have to write beginning mass, ending mass. I just tare it, and it subtracts it automatically, and I go reset the machine to 0. Now, if I wanted to, for example, weigh this bottle on it, I'd have to re-zero it to nothing on it, okay? So what it's asking me to do is to measure the mass of 50 drops. So I have a dropper here, and I am going to count to 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 40. 1, 2, 3, 6, 7, 8, 9, 10. Oops, I want an extra drop. So it was 2.3 grams, and the drops there, 50 drops weigh 2.3. To save time and to save your agony from having to do this, I've already measured 2 other cups. So this is my third cup. It weighed 2.3 grams. And what I want to do with this is take an average, okay? So if I'm going to take an average and I'm going to use my calculator, I'm going to need my glasses. It asks me to divide the mass of the water by the number of drops. So if you add these up, you get what? 6.8. And if you divide that by 3, that gives me an average mass of 2.27 grams per 50 drops. And if I divide that by 50, I end up with 0.0, some numbers, 4535 or something, 0.45 grams per drop. And that is my answer, our answer today. If you did it, you might get a different answer, okay? Lots of variables here. What size drop are you using? What size opening does it have? we're pushing it out, and so the humidity and the pressure, the barometric pressure that day, will affect the drop size. We traditionally say there's about 20 drops per gram, so it would be 0.05. That's just the estimate we use when we're doing rough calculations, but it depends on the person, the dropper, maybe the pressure you're exerting, how much water and back pressure you have in that pipette, but that's our answer. And so, we will go on, and it says, determine the mass of a pre-1982 penny and a post-1982 penny. And so I have some pennies here. Here's some pre-1982 pennies. And on average, they don't weigh 1.7 grams. What did I forget to do? The tare was already set on here. Let me zero my balance to 0 grams. And this one weighs 3.1. This penny weighs 3.1. This one weighs 3.0. That's very unusual. 3.0. Let me re-zero, make sure I'm getting everything right. 3.1 and 3.1. So, when I did it before, every other one was weighing 3.2. I might have been using a different balance. 3.0, 3.1, 3.2. So this balance might be calibrated a little differently, 3.2. So I was using this balance. Every other one was measuring 3.2. Not every other one, but in general about half of them. And so, I had these different values for my pre and post 1982 pennies, and we're going to discuss that. So, let's answer our questions. It says, what is the average mass of a single drop of water in milligrams? So, I've already done that. I have my measurements here, and this is the measurements you put up above in the data section. These are the measurements, this many grams in each case per 50 drops. So I can do this average several ways. I can go ahead and calculate the mass per drop and then add those up and divide by the number of experimental trials, or I can just do my easy math, add up the numbers that I got, divide by 3. I could increase my accuracy maybe if I did it 5 or 10 times, and then divide that average for 50 drops by 50 drops to get my mass per drop. So this is the analysis question 1. A1. This one was 2 over here. This one was 1. So that's my answer for that. And then they want it in milligrams. So here is my 0.045 grams per drop. That's a G. Grams. Times 1,000 milligrams per gram. Okay? My grams cancel. My answer is in milligrams. And if you measure 0.045 by 1,000, you will get 45 milligrams. Okay? So, there was a conversion for you. We calculated our value in grams, because that's what we measured. But they asked us for it in milligrams. In question number 1, 1,000 milligrams per gram, we did our dimensional analysis, our canceling. We multiplied this value by 1, because this is really 1 over 1. 1,000 milligrams is the same as 1 gram. We don't usually write it, it's understood, but we just multiplied by 1. So in question 2, it asks us, the density of water is 1 gram per cubic centimeter. calculate the volume of a single drop in cubic centimeters in mil. So this is A2. So our density is 0.045 grams per cubic centimeter. I'm sorry, grams. And the density of water is equal to 1 cubic centimeter. I don't want to equals there. But 1 cubic centimeter of water weighs 1 gram. In this case, my grams cancel. I'm just multiplying it by 1. So if I have 0.045 grams of water, I have 0.045 cubic centimeters. Okay. And if I have 0.045 cubic centimeters of water, and I want to convert that to milliliters, as the question asks, I multiply it times 1 milliliter per 1 cubic centimeter. And again, it's 0.045 milliliters. Okay? And here's why. Whenever we're dealing with water, I love dealing with water because a block, a cube, 1 centimeter on edge, so 1, not a 7, and 1 centimeter, so it's equal to 1 centimeter cubed. That's also equal to 1 milliliter at 4 degrees Celsius, the densest point of water. And it's also equal to 1 gram. I don't know about equal, but it corresponds to 1 gram. Okay? It's the same as 1 gram of water. If I take that cube of water, it will weigh 1 gram. So the last part of this said, what's the volume in microliters? There are 1 million microliters, given that prefix, in a liter, and 1,000 milliliters in a liter. Milli as in millennium or 1,000, micro as in 1,000,000 in case of our terminology and our definition. So there are 1,000 microliters in a milliliter. So if I have 0.045 milliliters and I multiply that times 10 to the third, or 1,000 microliters, remember that's a Greek letter mu, it's a U with a tail, per 1 milliliter, then I will find that this is 1, 2, 3, 10, 100, 1,000 is equal to 45 microliters. And there's your other answer. So, these are your answers for question 2. I know I'm giving you all these answers, but I think we need to discuss these and give you some help with these. The next question asks, what is the density of water in milligrams per cubic centimeter and milligrams per mil? Personally, I hate questions like these because these are just theoretical, intellectual exercises that I would never do in a practical setting. So they want density in milligrams per cubic centimeter and milligrams per mil. Second part is easy. Milligrams per cubic centimeter. So we know that the density of water, and it was given to us up above, I want to say in the text somewhere, is 1. But that, if I can get to it, oops. Sorry, but my mouse is catching on something. So, density of water is 1.00 grams per cubic centimeter. And it asks in the next question, number 3, what's the density in milligrams per cubic centimeter? Well, that's pretty easy because all we need to do is convert grams to milligrams and leave the cubic centimeters alone. So there are 1,000 milligrams in a gram. So my grams cancel, and I will have 1 times 1,000, or 1,000 milligrams per cubic centimeter. Or if you would prefer, 1.0 times 10 to the third milligrams per cubic centimeter. And we already said that 1 cubic centimeter equals 1 milliliter. So I'm just going to swap these units out and do the same thing and say this is 1,000 milligrams per milliliter. Or if you want it in scientific notation, either way, 1.0 times 10 to the third milligrams per milliliter. I don't have to do the conversion. I had 1.0 times 10 to the third milligrams per cubic centimeter, and I can multiply that times 1 cubic centimeter per 1 ml to get rid of my cubic centimeters, and that would give me my 1 times 10 to the third. This is the one, my marker is giving me extraneous marks. Would give me the answer if you want to do the conversion. But you know a centimeter equals a mil. And then we have some discussion of our pennies that we measured, and 3 questions about the pennies. Let me go ahead and take this off and answer those questions quickly. It says, pennies made before 1982 are 95% copper. Question number 4. 95% copper and 5% zinc. Copper is Cu, zinc is Zn. Copper is a transition metal, element number 29. Zinc is element number 30. They're right next to each other in the periodic table. Here is a mole, a quantity of copper, pure copper. Here's a quantity, a mole of pure zinc. It's less dense than copper. But you can see they have very similar molecular weights, atomic masses, but quite different volumes. But 2 very common metals used in a lot in industry, used in minting. And copper, I always learned it was 97 and 3%, but it says in a pre-1982 penny, calculate the mass of copper and the mass of zinc. Well, I looked it up on the internet, and pre-1982, or 1982 and before, pennies, technically cents, pennies are an English unit. If you look on ours, it says 1 cent, not 1 penny, 1 cent is its formal name. They have a mass of 3.11 grams per cent. Okay? So each cent weighs 3.11 grams. So to calculate how much copper is in that, if it's 95% copper, we just do 3.11 grams times its fraction, 0.95, 95%, and you will find, if you do the math, plug it into your calculator, I've already done it, that comes out to 2.95 grams of copper. And for the zinc, 3.11 grams times 0.05, 5%. So 5% of this 3.11 grams is zinc. That gives me a mass of 0.16 grams of zinc. Beautiful coins, very resistant, made of copper. If you look at the next question, it says pennies made after 1982 are made of zinc with a thin copper coating. We're going to dissolve away the zinc in the lab and make something called a copper foil in another experiment. When we look at reactions of metals with acids, we're going to dissolve the zinc in an acid, hydrochloric acid. which doesn't dissolve copper. So two different metals with different properties. One dissolves in hydrochloric acid, one doesn't. But the new pennies are 97.6% zinc, and 2.4% copper. Remember, I make my Z's. I grew up in Europe, went to school in Europe, and so I make my Z's like this, and I call them a Z, like the rest of the world. But so a Z has that. That's just our American letter Z. But post 1982 pennies only weigh 2.5 grams. I'm sorry, American cents per cent coin. So to calculate the amount of copper in there, I would take my mass, 2.5 grams, times 0.976, the fraction of it, that's actually zinc. Oops, that would be zinc. Let me do my zinc first, my primary metal in the coin. And I get 2.44 grams of zinc in every penny, okay? And then for copper, 2.5 grams times 0.024%, or fraction, 2.4% or 0.024 fraction, and that would be equal to, and I did the math on that, 0.06 grams of copper. A lot less copper. So it says, why does one penny have less mass than the other? And here's why. If you look down here at zinc, it has a density of, it's very small, 7.14, and copper has a density of, I think that says 8.95, but my point is the copper is more dense than zinc. So if you have more copper, you're going to weigh more. The mass of copper present is going to be greater, and the mass of the coin is going to be greater. So for our final question, it says, why does one penny have less mass than the other? Because it weighs less. Shouldn't start a sentence with because, but I'm running out of room. The post 1982 pennies weigh less because post 1982 pennies, cents, have more zinc, which is less dense than copper. Interesting fact, you want to guess why they switched from copper to zinc? I think it's pretty easy. It's economics. It cost about 3 cents to make a penny. And what do people do with them? Throw them in the cup holders in their car, throw them in top of the dresser, and if you look in my lab, you throw them in the big old Ozarka water bottle. That's my retirement fund. And I'm accepting contributions. If you save your pennies, I'll be happy to take them because I use them in the lab. And some of them I use up because I want to show you a modern penny. So we may have to get close on this, but here's a modern penny. I have a pair of Stanley tin snips here. And I'm going to cut this penny in half. And for this, I will put on my safety glasses. But I'm going to cut this penny in half and show you, I hope you can see, the inside is silvery zinc, and there's an extremely thin copper coating. We're going to separate these two components of pennies. And by the way, what I did was not illegal. You can deface a penny or destroy a penny. You just can't do it for profit. So I can't, for example, take the copper off, leave the silvery colored zinc behind, and try and pass it off as a dime. But I can use it for research and teaching purposes. So clearly not copper. And here's an old copper penny, 1982 or before. But watch what happens when I cut this one in half. We already know it weighs more, it's denser. It has a different sound than the modern penny. And when I cut the old penny in half, you'll see the center. One thing, it's a little harder to cut because it's pure copper, which is different. And the inside is beautiful copper. Okay, so save your pre-1982 pennies because they're worth even more. It is illegal to melt them down and sell that copper, although you would make a profit. But many people are saving their pre-1982 pennies, hoarding them, in hopes that that law will be changed or that the penny will stop using the penny the way Canada did a few years ago, and then they can melt their pennies down. And this that costs them 1 cent is going to get them 4 or 5 cents worth of copper. So, answer your questions in your report. Submit it to me. We'll get you some more credit for a lab. I'm sorry we can't do this in person. Anytime you want to come by and come in the lab, later in the semester, you want to do this experiment or any of these demos I'm doing, we'll go back to the back of the classroom. I'll get things set up and we'll do them. But until we have a vaccine and the ability to work closely together, that's just not going to happen. So I hope these virtual labs give you a little introduction to our world of chemistry. It's not entirely satisfying for me, but it's better than nothing. So until the next video, stay safe.